introduce Yimin Xiao from Michigan State University for the last talk of the day with a time difference of what, 8 hours? 8 hours probably. And so he's going to talk about fractal and the intersection properties of Lévy processes with a potential-theoretic approach.
Thank you, Stefan. I would like to thank the organizers for giving me the opportunity to participate in this very stimulating workshop. And it's a great pleasure to give a talk at the workshop. So as you can see from the title, that we're going to look at some fractal and intersection properties of Lévy processes. And the method that we'll be using will be potential theory of Lévy random fields. Most part of this is based on joint work with Professor Dava Koshnavisan of University of Utah. And then the later part was based on some results obtained with Thomas Lucas, who was visiting Michigan State University a few years ago. Here is an outline of what I am going to present. And we give some examples of how fractal sets arise from Lévy processes, and actually can arise from many other stochastic processes as well. So my hope is that some of the methods developed for Lévy processes might also be useful for more general, let's say, Markov processes or some other processes. And we are going to look at mostly Hausdorff dimension of those random sets. And as we know that Hausdorff dimension there is closely connected with capacity. So sometimes we are also able to get information on capacity, and it goes both ways. So as we will see. Now the main tool that we'll be using will be a potential theory for multiparameter Markov processes. I would say a class of multiparameter Markov processes. And this will be the so-called additive Lévy process. So it will be the additive Lévy process that we'll be focusing on in the main part. And then we take the results that we obtained on potential theory of additive Lévy processes and then apply them to solve some problems regarding ordinary Lévy processes. So that's the main theme of today's talk. I don't think that I will be getting to section 6, but just for completeness, you'll see section 6 is related to some of the potential theoretical problems. So to complete the answer for 3 questions, I include this section over here. So let me start with some preparation, and I'm sure that in the audience there are experts on Lévy processes, Markov processes. So this first couple of slides may not be necessary, but for notations, let's say consistency, maybe I just make an introduction on that. So we'll be mostly working with the Lévy processes. So these will be processes with stationary and independent increments. And we assume that the processes will start from 0. And then for Lévy processes, a very important tool is the characterization using this Lévy-Khinchin formula for the characteristic function of a Lévy process. And so we're going to use actually this exponent, so Lévy-Khinchin formula, a lot. Most of the results we will be stating, they are in terms of this exponent. This is called the Lévy or characteristic exponent. And of course, in this expression, there's also a Lévy measure. So many of the properties can also be expressed in terms of the Lévy measure. But most conveniently in analytical ways, in this talk, as you will see, most of the results will be described by using the exponent psi. All right. So what are the objects that will be of interest to us? Well, we are interested in some sets, random sets generated by the sample functions of a Lévy process. So if I have a Lévy process Z, right, I got this sample path. I could look at its range, or I could look at its trajectory, or let's say the graph set, right? And this 0-1 interval, time interval, is just chosen for convenience. Later on, it could be something very general. For example, I list also here, you can replace the 0 by any, let's say, Borel set E, and you can study one or whether the image will intersect another set F in the state space. right? So, so these sets, whether they are empty or not empty, many times this could be an issue, right? For example, in this case, this definitely can be an issue. So is the case of, let's say, inverse image or the level set and so on, right? Sometimes, the level set, which corresponds to the case F is a singleton, could be empty. Now, if it is empty, of course, there's no further question asked on the fractal properties. But we also know that sometimes it may not be empty. So in that case, we care about their, let's say, fractal dimensions, right? How big they are and things like that. And the intersection problems can happen, in various ways. And here I say it's an intersection between the image and a fixed set. Or sometimes it could be intersection of the sample path itself, self-intersection. Or sometimes it could be intersection of, let's say, independent sample path of different Lévy processes, right? So as you can see that these are just a few examples of random sets that can be generated by Lévy processes, and various kind of questions can be asked. And some of the, let's say, whether a set is empty or not, whether, let's say, this is empty or not, whether this is empty or not, this is related to the heating probability of, let's say, the Lévy process under consideration. Now, there's a long history on this topic, and it goes all the way back to Paul Lévy and James Taylor at the beginning of the 1950s. They studied the related problems for Brownian motion. And then in the 60s and on, many people extend them to Lévy processes, and various kind of indices were introduced, and people use those indices, up indices, lower indices, and so on to describe fractal dimensions of, let's say, the image of a general Lévy process. Now, more recently, I think there'll be, very important Markov processes have been under intensive investigation by different groups of people, and failure processes associated with, let's say, differential operators. Right, I learned from that from Professor Neil Jacob and Rene Shinin, and also I was very lucky to be in a conference at Warwick in at the beginning of the 2000. Professor Prof distributed a reprint of his paper on stable-like processes, stable jump diffusions. So that's a very interesting paper. I learned a lot from that. And more recently, there have been SDEs driven by Lévy noises. And so all this active research stimulate more questions regarding, let's say, how much we know about their sample path properties, how do we relate them to fractals, and so on. So, so I hope that some of the things that we're going to present regarding Lévy processes could shed some light over, possible approaches for studying those problems. Now, I listened to a very interesting talk given by Dr. Xiaochuan Yang about 10 days ago. In which he presented some Hausdorff dimension results for Lévy processes, uniform dimension results even. There, he introduced, he gave a very nice introduction on Hausdorff dimension and capacity. So what I'm doing here is just, for the notation convenience, just introduce what they are, and we can go through this pretty quickly. So the main tool we will use is the Hausdorff dimension to describe the size of a set. Right, and for the definition, we are very familiar with that. Let's say we define beta dimensional Hausdorff measure of a set to be the limit of the infimum of those sums associated with the coverings of the set. So I start with the sequence of balls of small radius to cover the set E, and for each of these balls, I compute, this fractional power, possibly fractional power of this 2Ri, and add them up, right? And I look for the smallest or most economical covering of the set, and then let epsilon goes to 0, take a limit. It turns out that, of course, this limit does exist, and the set function we define this way is indeed let's say, a metric out measure. So, so we know a lot of things about that. And then the Hausdorff dimension is just a quantity, describes, a geometric character of this set E. which is to say that this is a number, it's a critical value, to the left of this critical value. If you use that kind of beta, you would get.
Yeah, it's called it.
Say it again.
Sorry.
Oh, I'm sorry. Yeah, I missed it. And this is a familiar definition of Hausdorff dimension that we will be using. As Xiao already pointed out that in order to compute or estimate Hausdorff dimension of a set, normally there are like two parts of it. One part of it is to get an upper bound, and then the other part of it was, is to establish the lower bound. It turns out that for establishing the lower bound, the so-called capacity argument is much more convenient than using the definition. Right. So for that purpose, we're going to introduce what we mean by, we have a capacity, what the capacity argument is, and how we're going to use this argument. All right. So in order to introduce this notion of capacity, we start with, let's say, a Borel set, or you can start with a compact set. And you have a family of, let's say, all Borel probability measures carried by the set F. This is denoted by PF. And for every measure, if you have a kernel F, or in this case, we actually choose a special kind of kernel because this kernel does not have to be like of the form of a function of x minus y. It could be more general than that. But for our purpose, since we're dealing with Lévy processes, this is sufficient. So if we have a function f, non-negative, and then this double integral over here is called the energy integral of this measure with respect to the kernel f. So it's the f energy. And if it happens that I take the infimum of this energy of all possible probability measures on f, this, I take the reciprocal of that, that's the capacity. So, so what we care about is whether this capacity is a positive or whether this capacity is a zero. So as you can see, in order for this capacity to be positive, it is necessary sufficient that there is a measure mu for which the energy is actually finite, right? So this comes up very frequently in arguments. We're not going to work with very general kernel f. Since we are computing dimension, right? So mostly we will be working with a Ritz Bessel kernel like that, Bessel-Ritz kernel like this. So if we do use this kernel, then we denote the capacity by C beta. So beta is the negative power of the kernel function. Now, what we're familiar with is that there's a connection between Hausdorff and the capacity dimensions that was established by Forstmann a long time ago. So as Xiaochuan Yang said in his talk, now the direct argument for proving some set has a dimension gamma. Normally, you could break this proof or determination into two parts. First, to show that there's an upper bound like this. This can normally done by getting a suitable covering for the set, and then you use a capacity argument or some other argument try to establish the lower bound. So this is a very extensively used method and it's very powerful. But unfortunately, in order to use this method to get equality of this kind, normally the set you are dealing with, or the underlying process, Lévy process, let's say, because this f could be the range or graph of a Lévy process, right? So if that's the case, you would need your process to have some approximate scaling property. If your process lacks of scaling property, then even if you use this method, it is likely that the upper and lower bound that you can derive, they may not agree with each other. So that's a problem using this direct approach, which is to say, often we're not able to get the equality for the Hausdorff dimension of the set of interest. So some other approach might be desirable, right? So that's what I said in the title. We're going to use a potential-theoretic approach to derive, fractal dimension of a set without have to require the set has any kind of, scaling or approximate scaling property. So that's the advantage that one will gain by using this different approach. Now, this approach actually is quite old. It's quite old. I think the first time I saw it was used by James Taylor in his 1966 paper when he was studying the multiple points of a stable Lévy process. Right? It was based on, again, based on this Frostman's theorem saying that the Hausdorff dimension equals to the capacity dimension, right? So if we break down what Frostman theorem says, we can see that, well, it says that if the capacity of set E is bigger than 0, then the Hausdorff dimension of set E will be at least, beta. That's one way. And then on the other hand, if the capacity is 0, then the Hausdorff dimension of E cannot be bigger than beta. So this is to say that in order to decide what the Hausdorff dimension of a set is, you look at the capacity of this set to see when it is positive, when it is negative. So by saying one is positive or one is negative, what I meant is that, well, you see for which beta, right? The beta dimensional capacity or the capacity of beta order is positive, or for which other beta that the capacity of order beta of E will be 0, right? And it turns out that there is a probabilistic description of such phenomena by using stochastic processes, right? This is based on some well-known result regarding heating probability of, let's say, Lévy processes. They were established, as far as my history may not be totally correct. As far as I remember, it was like already considered these subordinators, stable subordinators, and then Kanda symmetric alpha stable, and so on, and Hawks for more general Lévy processes, and so on. So in any case, there's a beautiful result relating whether the capacity of set is positive or 0 to whether a stable Lévy process will hit this set or not, right? So I quote this theorem over here just to use it to illustrate what this co-dimension argument is. All right. So let's see what it says. I have a Z sub alpha. This is a alpha stable Lévy process, the strictly alpha stable Lévy process. And alpha is the stability index. Of course, it's between 0 and 2. And then if you want to ask one or whether this probability is 0 or not, right? There's a criterion for that. The criterion is that this thing is 0 or not 0 based on whether this capacity is 0 or positive. So this is a necessary and a sufficient condition. Then we can translate this, this is a potential theoretical result, right? We can translate this result by saying that, well, if I use a alpha stable Lévy process and try to hit this set F, right? If this F can be hit by this Lévy process, in this sense, there is a T such that ZT lies in F, right? By that, I mean, the process hit the set F. So if it hits, then the capacity in this order, D minus alpha of F will be positive. On the other hand, if you send out a strictly stable Lévy process, let it grow, and it never hits this fixed set F, then the capacity of this F will be 0. So capacity positive or 0 really depends on whether a Lévy stable process can hit or not hit this set. So this makes it possible to describe the dimension of F in terms of whether you can find a alpha stable Lévy process to hit this F or not. So in other words, whether F is polar or non-polar with respect to an alpha stable Lévy process. So a straightforward capacity argument, right? Because the capacity argument basically is here. It says that capacity positive or negative decides what the Hausdorff dimension of the set is. So if we use this idea and combine with this probabilistic result, we see that the Hausdorff dimension F equals to because this is D minus alpha, so D minus the infimum of this thing over here. So that's a very powerful method that's used initially by James Taylor And then John Hawkes made beautiful applications of this argument to talk about the inverse images of a Lévy stable process. And then Yuval Paris used a similar idea, but he did not use stable Lévy processes. He used the population sets as in place of the range of a Lévy process. And then Davar Koshnavisen, Davar, and myself, we did some work on there. So what we will explain is related to the later work done by Davar Koshnavisen and myself together. Now, I want to point out that as useful as this core dimension argument or potential or this, core dimension argument is, this expression over here is that there's a restriction. Because we know that for alpha stable processes, right, the index can only lie between 0 and 1, cannot be more than 1. That is to say that in order for this formula to be effective, to be useful, right, because you want to show that the dimension will be d minus something smaller than or equal to 2, that means that this formula can only be used for fractals which has a dimension bigger than d minus 2. So this is a restriction if you want to use this method. And of course, there are many sets of interest that this condition does not satisfy, right? So this raises some question to see, well, if you want to expand this co-dimension argument, it seems like you cannot just use alpha stable Lévy process as your testing tools. You have to have some more general testing tools allow you to detect the sets with smaller dimension. Right? Put it in the other way, I say that, well, a more general potential theory is needed. Right? So as a testing tool, and your tool should be able to detect the larger sets, small sets, all the sets of interest, right? So alpha stable Lévy process cannot fulfill this goal because alpha lies between 0 and 2, right? So this is the motivation for us to study, let's say, a potential theory of multiparameter Markov processes. But historically, potential theory of multiparameter Markov process, they were studied a long time ago. Davar Koshnavisen and I, we started in the 2000, 2002, and so on. And then there are several groups of people, they studied potential theory of multiparameter, mostly multiplicative Markov processes, to solve problems related to Lévy processes. I will show you one example like that. Steve Evans, has series of papers. Fiesmont Salisbury, the famous paper, 1989, and Hirsch and Song, they had a series of papers. So our interest was to use the so-called additive Lévy processes. We try to develop heating probability and the related problems for multiparameter Lévy processes defined by just adding up a few independent Lévy processes. It turns out that the additive Lévy processes, they are more general than multiplicative Lévy processes, because a multiplicative Lévy process, we will see, can be written as an additive Lévy process as well. We studied some of the potential theoretic problems in the early 2000s. There was an extra condition we were not able to get rid of. And finally, in 2009, we got rid of that condition. So the general results that I will be presenting, they came from this 2009 paper with Professor Davar Koshnavisen. All right, so this part that I am going to explain what an additive Lévy process is. And to describe its potential theoretical results, we focus on a few related ones, right? So, and now I show you what the main result is in this respect. And then finally, I move to the next section to show you how to use the result to derive fractal properties of let's say, of Lévy processes. As I said, to define additive Lévy process is to add up a few independent Lévy processes using different time parameters. So x of t here will be a random field. This is m parameter, m variables, taking its value in RD, right? So this is an ND multiparameter Lévy process. So we call additive Lévy process. We will use, when we develop theory, we do it for general Lévy processes. But when we try to use the theory to making this co-dimension argument, as I showed in the previous slide, we focus on using simpler ones because as tools, right, to detect whether a set has a positive capacity or negative or zero capacity, the simpler the tool, the simpler the better, right? So we take the tools to be a class of additive stable processes. So in other words, we're going to take each of these XJs to be an isotropic alpha stable Lévy process. So there will be a corollary for that class of process, and then we use that class of process in place of the alpha stable process that we saw in the previous corollary for the co-dimension argument. I said that, well, multiplicative Lévy process, right, can be written as an additive process, right? Because you know, this the x1 t1 x2 t2, you just write them separately with a lot of zeros, right? So the first one would be just x1 t1 and the others are 0. The second one will be 0 x2 t2, the other, you know, coordinates are 0, and then you add them together, you get an additive Lévy process. But at the same time, it is also this multiplicative Lévy process. Now it turns out that additive Lévy processes is not only useful for developing some tools for determining the fractal Hausdorff dimension of certain sets, right? It actually comes up naturally in various contexts. I here give one example. The example is to study intersection of Lévy processes. So I can start with n independent Lévy processes, x1, x2, and xn, and then ask the following two questions. One question is that, do these n trajectories intersect or not? So in other words, now, can you find different? Can you find time epochs at which the values of the process equal each other, right? The sample path intersect at those time points. When they do intercept, then you get a set of intersection, either in the space, or you can talk about set of intersection of time. And then these usually are pretty sparse sets, so you can ask their fractal dimensions, right? So these questions can be asked, can be studied. And one way to study them is to translate these problems into a problem regarding additive Lévy process. And how does an additive Lévy process get into the picture? Well, we can define x2 t2 minus x1 t1, x3 t3 minus x2 t2, and so on. Then the sample path will intersect in this sense over here, means that this process has a non-trivial zero set. The level set at 0 will not be empty, right? So intersecting problems is reduced or equivalent in this case to the non-emptiness of the zero set. So to study the intersection of, let's say, sample path of independent, Lévy processes, this problem is reduced to studying the zero set of an additive Lévy process. So it does show up in different contexts, but we will be only focusing on some potential theoretical issues related to this class of multiparameter Lévy process. I ask three questions and provide answers for them. So the first question is that if I have a target set in RD, and I wonder, if you let your process run on your index space, is it possible that the range will actually eventually enter the set F, so intersect this F with positive probability? I took away this 0 point because at 0, it is 0, it's deterministic. So if this set F contains 0, then the answer is trivial, right? So we'll try to get rid of that triviality. So this is first question, is a heating probability problem. And as you can see, if this X is a stable Lévy process, then the answer to this question is known, right? If and only if F has, D-2 dimensional capacity, right? But for a multivariate Lévy process, so the answer is, in general, it was not known. So we asked that question. We try to study that. And a related question is whether same sets F and the range. You add the members, the elements of the sets together, you form a larger set. And you wonder if this set has D-dimensional positive Lebesgue measure. You could ask this question. And it turns out that these two questions are very closely related. I will show you in the next slide what the exact relation is. The third question is, any kind of random set, whether this is the range or whether this is the graph or whether this is the level set, right? You can always ask whether this random set intersects another set or not. So here I choose the level set of this process, and this level set is a subset of the index space. So I get rid of the trivial parts, the origin and the boundary maybe, and I just take the part in the first quadrant. So if I take a set E from the first quadrant, I wonder whether your level set can intersect that set E or not. So that's also a meaningful question, which is similar to the first question, except that the first question uses the range, the third question uses the level set. Now we know that if we are dealing with, let's say, ordinary Lévy process, then this A and C can be combined together because the level set is up to a countable set, right? It's equivalent to the range of a subordinator. So the heating probability of the level set can be translated into heating probability of the range of the subordinator. But in the multivariable case, like additive Lévy process, these two, you don't have this connection of the subordinator, so it has to be treated separately. So as I said that I will not have time to treat this last question, we'll be focusing just on answering A and B. But before we go on to provide results on A and B, I want to tell you a theorem of Gahan. He proved it for the case of n equal to 1, showing the connection of these three kinds of problems. And we extended with the Dvor-Koshnovison, we extended to additive Lévy processes, but the argument was pretty much the same as what Gahan did for Lévy process. But it's a very useful result, which is to say that if there's an extra condition on the Lévy process we have to impose, so the degeneracy has to be excluded, right? So we assume that the XT density is absolute continuous with respect to the Lebesgue measure, equivalent to Lebesgue measure. Under this condition, then whether with this one, that one, they are the same, whether the image will intersect the set F or not is equivalent to whether the difference set has a positive Lebesgue measure or not. So this 1 and 2, they are heating probability questions. And Gahan showed that, well, for Lévy processes, well, he did it for Lévy stable processes, it's equivalent. This heating probability question is equivalent to whether this difference set has positive Lebesgue measure in the state space. So that is to say that this two questions A and B, they are related, at least under the condition that the distributions are absolutely equivalent to Lebesgue measure. So we worked to provide a description of this answers to this question, and we obtained necessary and sufficient condition for those things to happen. And the necessary and sufficient condition is needed if we wish to establish, let's say, Hausdorff dimension results, let's say, for certain random sets, because we want both ways, right? Well, in order to decide the Hausdorff dimension, some less, let's say, stronger result may be sufficient, because I said that necessary and sufficient condition may be needed. I don't think that's a correct statement, because when you derive dimensions, you allow the upper bound and lower bound to be slightly different, and then you can apply a limiting argument to get equality, right? So in that case, if you have very close necessary condition and very close sufficient condition, you may still be able to do the job. But for us, we have necessary and sufficient conditions, so we can get the equality using the codimension argument. All right. So so for this first result, it is on whether this set has positive Lebesgue measure or not. Positive Lebesgue measure with positive probability, let's say. Here, of course, it's the plus sign. The plus sign or minus sign doesn't matter, right? Because the Lebesgue measure is nice. And so this is a necessary and sufficient condition. So in order for the left-hand side to be true, it is if and only if you can find a measure, probability measure on F, so that this is also a kind of energy. This is a Fourier analytic energy instead of like the energy we saw before is a convolution-based energy, right? So this is an energy of this measure mu, and this is the Fourier transform of that measure. And these guys are the exponents of the Lévy processes x1, x2, and xn. So as you can see that it is the exponents of those Lévy processes that completely decides whether, right, whether this thing is true or not. Now, if you look at this result had a long history for Lévy processes. For Lévy process, this is the result of Kasten, very important result of Kasten regarding polarity of singletons. He established in 1969. And then John Hawkes realized that a condition is equivalent to the existence of local time of Lévy processes. So he provided a criterion for the existence of local time, which is also in this form, using this kernel over here. And our result here is a multivariate version, a multi-parameter version of the earlier result of Kasten and Hawkes. All right. Now, of course, this result here provides a criterion on the Lebesgue measure of the range, plus a fixed set. It doesn't answer the question whether this is a hitting probability, there is a hitting probability or not, right? So using the result that extends the result of Gahan, we know that we need some assumption on the distribution of xt, right? If xt is, let's say, the distribution is equivalent to the Lebesgue measure, then we can translate this result into hitting probability issues. But I don't need those general results. For today's talk, what I need is that I want to decide, fractal dimension of various kind of random sets related to Lévy processes, right? So I need a set of tools to do the job. So I choose the set of tools as, I skip this ideas of proof because there's no need for that. We're going to take this set of tools as alpha stable additive alpha stable processes. And I let this alpha to be arbitrary, let this n to be flexible for me to choose, right? And then you will see that the advantage you'll gain to have this flexibility, all right? But first of all, using the previous theorem together with the lemma in the previous slide, we see that all these three things are equivalent because alpha stable processes, they have density and so on. So all the conditions are satisfied. And we can say that this is true if and only if the d minus n alpha order or dimensional capacity of F is positive. F can be hit by X if and only if this F has this positive capacity. So it does become a hitting probability criterion. Well, since now it is a hitting probability criterion, right? I can go back to what the Taylor and Hawkes did in the earlier days, look at the co-dimension argument. So there's an analog of Crowley 2.2 that we saw before. Now this time, this is a general formula. It says that for any Borel set F of interest, if you wish to decide the Hausdorff dimension of this set, all you need to do is to come up with a whole bunch of additive stable processes with possibly varying index alpha, right? So that you decide when this additive alpha stable process will be able to hit this set F, and when it will not be able to hit that set F, right? Then there is a cutoff point at which, if it's on this side, it doesn't hit, and it's on that side, it does hit, right? If you can do that, then you get the Hausdorff dimension of this set F. So this is the so-called co-dimension argument. Now, I have the flexibility in choosing my n and choosing my alpha. So this n and alpha can be chosen arbitrarily close to D. So I can deal with all kinds of, any kind of Borel set. Does not have to assume that the set has a dimension bigger than D minus alpha, like in the previous slide. So this is the basic idea. And I've got a set of tools, right? This set of tools are additive stable processes. I am going to use this additive Lévy processes to try to use them to hit a set of interest, to see whether the heating happens or not, right? If it happens, then it says that the Hausdorff dimension of the set will be bigger than or equal to something. And if it does not happen, then it says that the Hausdorff dimension of the set will be smaller than or equal to something. And I can adjust the parameters so that I will be able to get an equality. So that's the basic idea. And it turns out to be a quite convenient idea because it's an analytic idea. And the tools that we use are completely decided by the characteristic exponent, right? So if I have knowledge on the characteristic exponent, I will be able to carry out, right, this argument. So in the rest of my talk, I show you a few examples that we use this idea. All right. So the first example is we try to decide the Hausdorff dimension of the range of an additive Lévy process, arbitrary additive Lévy process with this exponent. This time I put them together is a vector exponent. All right. So it turns out that this dimension of the range can be decided by the formula on the right-hand side. So as you can see that it depends on the behavior of the exponent at infinity. And this is the bigger than one is one is nothing. One is away from zero, right? So it is the asymptotic behavior of the characteristic exponent of the Lévy processes that allows or characterizes the fractal dimension of the range. And since the graph can also be written as an additive Lévy process with some parts of the exponent to be degenerate, right? So it can also be computed from this formula. So this is a formula not only for the range but also for the graph and so on. In many situations, this formula can be explicitly computed. For example, if X, of course, is an alpha stable process, the computation will be easy. On the other hand, this X can have, let's say, operator stable, right? Or even if it's not operator stable, as long as there's some information about the tail behavior of the exponent, this formula still works. Right? Because it is the asymptotic behavior of the exponent at infinity, right? Decides whether this integral converges or diverges, which decides the dimension. And I only have one slide on which there is a sketch of proof. So I think this proof is quite easy to describe. So I would like to say something about that. So the way of proving it is intuitively simple, in the sense that I am interested in X, the range of X. In order to decide the size of the range of X, I come up with an independent alpha stable additive Lévy process, Y. Then what I do is that I want to use this y to heat this x. Heat or not, that's not an issue. So if there's worry about heating, there may be no heating. I just look at the range of this expanded additive process. I add them together, form this new additive Lévy process. And then this new Lévy process, right, is still additive process because the y is independent of x. And their exponents can be written out. Their exponents can be written out, right? And then I can use theorem 4.2. Theorem 4.2 says that I treat this guy as a deterministic set because of independence. That's my f. F plus the range of a alpha stable additive process has a positive Lévy measure if and only if, right? This set F has a positive capacity. That's the content of the corollary because I'm applying it to the stable process, additive stable process. So that's one side of the story. The other side of the story is that this thing over here, over O, right, is another additive process, is the m plus m parameter additive process. And the exponents are all known. So I can go back to theorem 4.1, theorem 4.2, to say that, well, this guy is positive if and only if this integral is convergent. Then I look at the beginning, I look at the end, and I try to match how this has a transition, right, going from 0 to not 0. Then that will give you what the dimension of the set is. So this is a typical argument in terms of using this co-dimension argument, right? And you use a family of random sets for which you can characterize quite precisely the heating probability of them, and they use those guys as tools to heat sets of interest, and whether they heat or whether they don't heat gives the information on the size of the set. So in particular, they help us to decide the Hausdorff dimension of the set. So, so this is the, I think I added this slide to just explain this argument. Byproduct of this formula is the formula for ordinary Lévy process, n equals to 1. So if n equals to 1, then the Hausdorff dimension of the range can be decided by this formula over here. That was actually a question raised by Pruitt in 1969, because he established the formula in terms of the so-called occupation probability, a sojourn probability, sojourn measure in here. But this probability may not always be easy to estimate, for a general Lévy process. So he asked whether there are more convenient ways to establish, a formula for the Hausdorff dimension gamma in this case. And he mentioned whether, the character exponent should be the appropriate tool to use, right? So, so as a byproduct, we did provide a confirmation to that. So later on, we applied this idea because this is an analytic formula. As long as we have information on the exponent, then we will be able to decide what this gamma is, right? So I did some joint work with my colleague Mark Michard and Peter Kern on operator or semi-operator semi-stable processes. So this is one application. Yeah, my time is running out. So I'm going to mention like 3 more applications. The second application is to decide the exact capacity of this range, and this E can be very general, not necessarily an interval. So if E is general, then we know that the Hausdorff dimension of XE is not easy to get. And there were efforts, I think Bromento and Kitu, they introduced several indices, upper indices, lower indices, and they gave very nice bounds on that. But they asked what the exact value of this thing is, or whether that thing depends just on E or on X in certain specific ways or not. So those questions were not easy to be answered by using the ordinary arguments for the Hausdorff dimension. However, with the tool that we have, we can answer it precisely. So this is the question that Bramento and Gattu raised. They say that, well, you know, there should be a quantity which only depends on x and e, which is a constant, such that this dimension is actually deterministic almost surely, right? So the approaches using covering or capacity argument are not able to get the answer in general, but with the potential theory argument, we can, you know, get to that. So I show you what that thing is. So here's the result. It says that the gammath order capacity is a positive, almost surely. There's a 0-1 law in there as well. If and only if the right-hand side holds. So if there is a measure mu such that this integral is convergent, then the capacity is positive. If it's not convergent, then it will be, you know, it will be of capacity 0. So as you can see that as this parameter gamma varies, right, the capacity of XE will either be 0 or positive. And then the cutoff value will give you the dimension of this XE. So this dimension of XE can be written in terms of this kind of energy type of integrals. So that's a second application using this potential theoretic approach. Third application is to study intersections of Lévy processes. Now, this problem has been studied for quite some time in the 60s and the 70s, 80s of last century. And for Lévy processes, it was eventually settled by Fismons and Salisbury in 1989 to give a necessary and sufficient condition for the intersection to exist. So the intersection is not empty, right? And what we did was that we were able to go one step further. We say that, well, you know, if we know the intersection does happen, right, then you can raise further questions. One question is, how big is it? What's the Hausdorff dimension of that? Or what's the packing dimension of that, right? And secondly, you can say, well, you know, if I fix a set F in Rd, does this set contain any multiple intersecting points of your trajectories, of your path? So in other words, you can ask whether this set Mn intersects that F or not, right? So we asked these two questions and we derived the answer for that by using this potential theoretic argument. In doing so, of course, there's some extra conditions that we have to put on the Lévy process, but let's ignore that part. Let's focusing on this question. So, given a Borel set, one can the set of intersections of these independent Lévy processes intersect within F. When can this happen with positive probability? Well, the answer to this is that this will happen if and only if there is a measure mu carried by F such that this energy integral is finite, right? So this is the Fourier transform of that measure mu, and these are the things decided by the components of your Lévy process. So this provides a necessary and sufficient condition. And then go on one more step, we can decide the Hausdorff dimension of the set, once again using the exponents. And this time, of course, still using similar arguments, right? Take this additive stable Lévy processes and try to use them to heat this Mn in appropriate ways, right? And then to go from there, derive necessary and sufficient conditions. So that will allow us to decide what the dimension of this thing is. Now, intersections, in this section, there are intersections of independent Lévy processes. Intersections can also be raised or considered for a single Lévy process. That will be called self-intersection, or sometimes if the intersection does happen, the intersecting points will be called multiple points in the literature, right? So the tools that we mentioned before can also be used to describe, results on that. So I actually going to skip this part. Okay. Yeah, I said I would skip the part 6. So I just maybe spend 1 minute to mention the result for that. For self-intersection, the issue of existence of intersection can be solved by using this potential theory type of argument. And we actually use this argument of Lagarde, which says that self-intersection issues for the existence can be reduced to the issues of intersections of independent Lévy processes by using the strong Markov property argument. So there's close analogy between what we got for independent, intersection of independent Lévy processes with the self-intersection. So the Hausdorff dimension of that is very similar to the previous case, except that here everybody has the same exponent because it's a single, right? It's a single Lévy process that is under consideration. And this formula has the advantage that it can be computed in many cases. And Thomas, Lucas, and I, we looked at, first of all, some operator stable processes, and then because of the asymptotic behavior, it was also understood for semi-operator, semi-stable Lévy processes. We were able to consider more generally the Hausdorff dimension of the multiple points of these Lévy processes. Now, the good thing about the result is that the result is explicit in terms of the eigenvalues of the stability exponent. So if the stability exponent is diagonalizable, then quite simple things could happen, and we can take advantage of the information in those operators, right? So with that, I think I stop here. Thank you very much for your patience. Thanks again for giving me the opportunity to be here. Thank you.
Thank you very much. So yes, so there are some questions in the room.
John Hawkes, who was a colleague of mine at the same department, proved his theorems about 40 years ago. I wonder in what extent they can be extended from strictly stable process to more or less general process. Is it true or not if we have a symbol which has the same asymptotic, like in stable case, the statement holds or not? Is it proved false counterexamples?
Yeah, I think in terms of this potential theoretical result, the result of Hawkes was quite general. I think it was for symmetrical Lévy processes under some actual conditions. And then the question that you asked maybe relate to one of Kanda's paper. He actually compared the character exponents. If the character exponents have certain relationship, then they would have similar heating probabilities. That's what I remember. So I guess the question to yours is yes. But I don't know how precise the results are in answering that.
Thank you. Is there another question in the virtual audience? So on my side, I have a question, Yimin. At some point, so you have a mu hat in your
I have
almost
a hat somewhere, yeah.
Yeah, somewhere. So this reminded me of the like the Fourier dimension. Yes. So yes. So okay. So yes. Okay. No. So it was at the end. Yes. Later there was a mu hat also in the formula.
Yeah. Yes. There was also a mu hat in the Hausdorff dimension of the sets.
Just
after
that.
Yeah.
So it's after that. Yeah.
The last one has one.
No, it's later. It's later.
Okay, it's later.
It's later.
So this
Next one, I think.
Okay.
One more.
Yes,
here.
there's one here, and the dimension. Yeah, there's only one here.
Yeah. So okay. So maybe it's not a clear question, but is there a relation with the Fourier dimension that is a? No. Okay. So okay.
Yeah, I think the Fourier dimension of the range definitely is an interesting question. I don't know the answer to that. And here, this is a measure on the set F, which
Yes.
which is in the state space. So this may not necessarily be related exactly to the Fourier dimension of the range or Fourier dimension of the intersection set. But nevertheless, the question you are asking is a very meaningful one, a very interesting one. For general Lévy process, I don't know the answer, actually. I don't know. I think Gahn did something for stable Lévy processes.
Mm-hmm.
He did something for fractional Brownian motion as well, stable Lévy processes. But I don't know anything going beyond that.
Yeah, including because the topics of this seminar is also Markov processes. So this cannot be generalized to even simple Markov processes.
Yeah.
Right?
Yeah.
No.
Yeah.
Okay. So are there other questions or remarks? Yes.
Hi, Professor. Xiaoshuan here.
Yeah. Oh, Xiaoshuan, hey.
So I have a question about the tool you mentioned in Paris did provide another tool,
Yeah.
percolation.
Yeah.
Use percolation set as a codimension, use that same codimension argument.
The
So
same codimension argument. Yeah.
Yeah. So in order to study a Lévy process and intersectional Lévy process, I think your arguments with this using stable process as a test set is very natural. But
Yes,
are there other examples where using percolation set is more natural?
Yes, I think Yuval Paris introduced the percolation sets for studying those random fractals constructed by using the iterative procedures, because the structure of an iterative procedure is similar to what the fractal percolation is, right? So I'll give you one example that I think you're familiar with, this limit soup random fractals. For limit soup random fractals, because there's no natural, Lévy process associated to this limit soup random fractals. What I said, using stable process will not be of any use there. But if you use this percolation sets to hit a limit soup random fractal, you can still use this codimension argument. So in terms of the example you ask, I give you an example of limit soup random fractal.
Thank you. So one last question or remark? No. So if not, we can thank Yimin again. And so thank the speakers of the whole day and also this nice discussion we had this afternoon. So that ends, that's the end for today. So see you tomorrow. Thanks again for Yimin for this very nice talk. And so we see each other tomorrow.
Thanks, everyone. Thank you.
Bye.